In this video, I will teach you how to find the relative extrema using the second derivative test. Relative extrema are the highs and lows of a graph, like these purple points right here. This point on the left is a relative max, down here at the bottom is a relative min, and this point at the top is another relative max. This point here at the top is also the absolute max because it is the highest point on the graph. But both can be true at the same time. It's the absolute max, but it is also a relative max. Relative extrema are sometimes called local extrema. So this would be a local max, a local min, and another local max. In previous videos, I've shown you how to find these relative extrema using the first derivative. But depending on what information you're given, sometimes it will be necessary or better to use the second derivative. So that's what I'm going to show you right now. To get to the second derivative, we still have to find the first derivative. So let's start there. F prime equals, doing the power rule, so this 4 is going to come to the front, reduce by 1, so we have negative 4x to the third power. Do another power rule on this term, and we're going to have 12x squared. Another power rule here, 2 times 8 is 16, so we have 16x. So there is your first derivative. Let's see if we can factor this. I see all of these numbers are divisible by 4, and they all have at least one x. So let's take a negative 4x out front and think about what's left behind. So we're going to divide everything by negative 4x. So this first term will become a positive x squared. The middle term will be negative 3x. And the last term will be negative 4. I'm betting we can factor this trinomial even further. Let's give that a shot. So we have our negative 4x. Okay, let's shoot for a binomial times a binomial. X squared can only factor as x times x. 4 can factor as 2 times 2, but it can also be 1 times 4. We need the inner plus the outer to equal the middle. So we'll need a positive 1 and a negative 4 in order to get this negative 3. Also, positive 1 times negative 4 is negative 4, so kabam! We factored it. Usually at this point, I would talk about the critical numbers that would make f prime equal to 0, or that would make f prime undefined. But when you are using the second derivative test, we are not interested in where the first derivative is undefined. So we're not going to find all the critical numbers. All we care about is where are the horizontal tangent lines. So we just want to know where the derivative is equal to 0. And we can tell that at a glance now that we have it in factored form. From the first factor, we have a horizontal tangent line at x equals 0. From the second one, there will be a horizontal tangent at x equals negative 1, and another one at x equals positive 4. Let's go ahead and put these on a number line. We don't really need the number line, I just want to illustrate something to you. Because the first derivative is equal to 0 at all of these values, we know that the function will have a horizontal tangent line at each one of these values. But the thing is, we know there's a horizontal tangent line, but we don't know if it's at the top of a hill like this, which would make a relative max, or is the horizontal tangent line at the bottom of a valley like this, which would make it a minimum. So you know what would help us out? Concavity. What if we knew the concavity at each of these points? If we knew that at negative 1 the function is concave up, then we would know that the horizontal tangent line is on the bottom. it's a min. If we knew that the function was concave down at 4, for example, then that would mean the horizontal tangent line is at the top. This would be a max. So we don't need the number line, but we will need the second derivative, because that's how we tell if things are concave up or concave down. Let's go back to this version of the first derivative for a moment, because it will be easier to find the second derivative from here. So doing that power rule, the 3 multiplies the negative 4, so we have negative 12x squared. The 2 multiplies the 12, we have positive 24x, and then plus 16. So this is the second derivative. Long ago, we learned that if the second derivative is positive, the original function is concave up. If f double prime is negative, then f is concave down. So we need to check each of these x values that we just found using the second derivative, and we need to see if the second derivative is positive or negative at each of these points. If we get a positive value, then we know that it's concave up. If we get a negative value, it'll be concave down. And we'll be able to tell if we're looking at a relative max or min. The first one is really easy because it's x equals 0. Let's plug that into the second derivative and see what we get. Well, these first two terms zero out completely, and we end up with f double prime at 0 is equal to 16. This is a positive value, which means that the function is concave up at x equals 0, and therefore we're looking at a relative min. So here's how you write up this answer and justify. You would say f of x has a relative min at x equals 0 because f prime at 0 equals 0 and f double prime at 0 is positive. Notice that we need both the first derivative and the second derivative in the justification. The f prime equals 0 part tells us that we have a horizontal tangent. The f double prime is positive part tells us that the function is concave up, and therefore it's a minimum. Next, let's check x equals negative 1. So we substitute that into the second derivative, and we just care about whether or not this is positive or negative. So if you take negative 1 and square it, that just becomes a positive 1. 24 times negative 1 is negative 24 plus 16. We don't actually care about the final answer, but at this stage it's easy to see that the answer is going to be negative. So f double prime at negative 1 is less than 0. That's all we need. In your mind, you should be thinking, okay, since f double prime is negative, that makes the function concave down. Therefore, the horizontal tangent line is sitting on a maximum. Let's write it up. You would say f of x has a relative max at x equals negative 1 because f prime at negative 1 is 0 and f double prime at negative 1 is negative. Notice that you need both of these. You need f prime to equal 0 and f double prime to be negative in order to conclude that you have a relative max. I was inconsistent here a little bit. To express the fact that f double prime is negative, I put less than 0. That's what I like to do. But on the previous problem, I said f double prime at 0 is positive. So just to be consistent, I mean, it doesn't matter which way you want to do it, but I should be consistent. So I'm going to go back and write f double prime is greater than 0. That's just another way of saying that it's positive. We got one more to check. Let's plug x equals 4 into the second derivative and see what happens. So that's going to look like this. So f double prime at 4 is equal to negative 12 times 16 plus 24 times 4 plus 16. We just need to figure out if this is positive or negative. You would get this, and it's pretty clear that the negatives are going to win this fight. So this stuff is less than 0, which means we are concave down, which means that we have a horizontal tangent line at a relative max. Let's write it up. So we would say f of x has a relative max at x equals 4 because f prime at 4 is equal to 0 and f double prime at 4 is negative. So one more time, the thought process behind this is the fact that f prime at 4 is equal to 0 tells us that we have a horizontal tangent line at 0. The fact that f double prime is negative tells us that the function is concave down, so that makes it a max. Let's do another. Before we begin, let's rewrite the function with a fractional power. So this is the same thing as x squared plus 1 to the 1/2 power. Now we can go ahead and find that first derivative using the power rule. Well, the chain rule, actually. So taking the derivative of the outer function, the 1/2 will come to the front. We have to subtract 1 from this, so think minus 2 over 2. So this will be the negative 1/2 power. But then we have this stuff on the inside. We have x squared plus 1. Because we have a function on the inside, the chain rule tells us we need to multiply by the derivative of the inner function. So that'll be 2x. So this is the first derivative, but we need to simplify this. Tell you what I'm going to do. The 2 that's over here in purple is going to cancel out the 2 in red, so those will be gone. The x is going to be in the numerator, but the rest of this is going to drop down to the denominator because of the negative exponent. So we end up with this. Remember, for this method, we don't care about where f prime is undefined. All we care about is what values of x will cause the derivative to equal 0, because that's where you have your horizontal tangent lines. A fraction will only equal 0 when the numerator is equal to 0. So we're just going to have one value to check, and that is x equals 0. That's our only horizontal tangent line. We just need to find the second derivative so we can figure out if the function is concave up or concave down at this point. To get the second derivative, I'm actually going to pick up from here with the first derivative again. So I have f prime equals, I'm still going to cancel out these 2's, right? The purple 2 and the red 2 in the denominator, those cancel out. But I'm going to leave x squared plus 1 to the negative 1/2 power. I'm not going to drop it down because it is easier to find the second derivative in this form. Because we can use the product rule and the chain rule. So according to the product rule, we start by taking the derivative of the first term. The derivative of x is just 1 though, so not very interesting. Then we multiply by the second factor left unchanged. So I'm going to multiply by x squared plus 1 to the negative 1/2 power. And then we put a plus, and we go through again. But this time through, we will end up taking the derivative of the second factor. We will leave the first factor alone. So I'm going to just leave the x right here. But now it's time to take the derivative of the second factor. So I'm doing the chain rule. The negative 1/2 power is going to come here in the front. So here's my negative, hold on, I'm messing it up a little bit. Here's my negative 1/2 in the front. I have to subtract 1 from this power. So think minus 2 over 2. So this will be the negative 3 over 2 power. negative 3 over 2. But then we have this function on the inside. So I'm going to just copy that down, x squared plus 1. But the chain rule demands that we now multiply by the derivative of the inner function, which is 2x. So this is the second derivative, but we've got some work to do to clean this up. Let me tell you what I did so far. I had this 1 in the front. We didn't need that anyway, so I just erased it. Over here we have the 1/2 and the purple 2. Those are going to cancel each other out. So that's why the 2's are all gone. This negative sign survives. That's why this is a negative right here. Then we had x times x, right? This x in the front, this x on the end became x squared. So that's what I did so far. It's time to factor. When you're doing the chain rule, you will very often come up with a common factor like this. We have x squared plus 1 here, and we have another x squared plus 1 here. Let's factor that outside of parentheses and put it in the front. So I'm going to have f double prime of x equals, and I'm putting this x squared plus 1 in the front. But what exponent goes on it? It's always going to be the lower exponent. So what's the smaller number? Negative 3 over 2 is less than negative 1/2. So that's the exponent that we're going to bring out, negative 3 over 2. Now we need to figure out what gets left behind inside the parentheses. Remember that when you factor something out, to figure out what goes on the inside, you divide. We're dividing everything. We're dividing both terms by this factor that we're pulling out. When you divide like bases, you subtract the exponents. So I have to subtract negative 3 over 2. Are you seeing the double negative that's happening? I have to go minus negative 3 over 2. But of course, when you subtract a negative, it is actually addition. So that's why you're going to see a plus 3 over 2 here and here. So negative 1/2 plus 3/2 is 2/2, which is really just 1. So that's why we're just going to have x squared plus 1. This is like x squared plus 1 to the 1 power, but we don't need to write the 1. Moving on to this term, you see the minus x squared, so I'm bringing that down. This factor is completely gone. You can either look at it as I took the entire thing, this x squared plus 1 to the negative 3 over 2 power, and here I have x squared plus 1 to the negative 3 over 2 power. I took the whole thing away. So that's one way to look at it. Or you can say we had negative 3 over 2 plus 3 over 2. So that's a 0 power, and anything to the 0 power is 1. So this is a 1 now, which we don't need to write. Either way is gone. So now we can just combine like terms, but actually it's pretty sweet because we have x squared and then we have negative x squared. So those are gone. So it's really just a 1 in here. But a 1 is something that you don't even really need to write. So that's why it's going to turn out that f double prime, whoa, that's heavy ink, f double prime is really just equal to the part that we factored out. It's really just x squared plus 1 to the negative 3 over 2 power. So we will be using this to evaluate other things in a moment. So it might be best to go ahead and rewrite this by dropping it down to the denominator. This is a negative 3 over 2 power. So this will be the same as having 1 over x squared plus 1 to the 3 over 2 power. So this is probably the version that I will use to evaluate. But remember, we only really had to check one value, x equals 0. So let's do that now. If we plug in 0, so let's find f double prime at 0. That's going to be 1 over 0 squared plus 1 to the 3 over 2 power. Well, everything in here is positive, so you know this is greater than 0, which means that the function is concave up, which means the horizontal tangent is at a min. Let's write it up. In fact, pause the video and see if you can write the justification on your own. Did your answer look like this? F of x has a relative min at x equals 0 because f prime at 0 is equal to 0 and f double prime at 0 is positive. Did you remember to include the statement about f prime and f double prime? Let's do one more. F prime of x equals. Aha! It's not very often that we get to do the quotient rule, y'all. Let's get it. Do you remember the quotient rule poem? Remember that when I say d, it means derivative. Low d high, less high d low. Draw the line and down below, the bottom squared will go. Know your quotient rule, y'all. Let's do it again. Low d high. When I say low, we're talking about just right down the bottom part. And then d high, the derivative of the top function, but that's just going to be 1. So that's low d high less high d low. So high is x, and then d low, the derivative of x minus 1 is just 1. So this is low d high less high d low. Draw the line and down below. The bottom squared will go. So this is the first derivative. Of course, I'm going to clean it up a little. Let's see. We have, well, we can just ignore all these little red ones. So we just have x minus 1 minus x. So the x and the minus x simply cancel each other out. So we will have negative 1 in this numerator over x minus 1 squared. Uh-oh. Uh-oh, people. Uh-oh. We are supposed to determine where f prime is equal to 0. We had one job. We had to figure out where f prime is equal to 0. But a fraction will only equal 0 when the numerator is equal to 0. But the numerator is a constant, so this has no solution. So now I got to figure out what to do with that. No solution. When this happens, it means that the second derivative test has failed. So we're going to use the first derivative test like I have shown you in previous videos, which I hope you watched. You know what? I'll put a link up here. If you're like, I don't know what the first derivative test is, what are you talking about? Go ahead and click the link that's going to appear up in the upper right hand corner right now. So when we do the first derivative test, we not only look at where the first derivative is equal to 0, but we also look at where the derivative is undefined. And we make a sign chart. So there are no places where f prime equals 0, but there is a spot where it is undefined. And that comes from the denominator, and we can see that at x equals 1, f prime is undefined. So let's put this on a number line and make a sign chart. So here's my number line coming along quite nicely. Here is x equals 1, my only test value, my only critical number. We will need 2 rows. I'm going to treat negative 1 as a factor, and I will treat the x minus 1 squared as a factor. So 2 rows. Be sure to label your sign chart as f prime. Now let's check each of these factors and decide if they are positive or negative in each interval. Of course, -1 is always negative, so bam, bam. But what about x minus 1 squared? Well, the whole thing is being squared, so guess what? That's going to be positive in every interval. So we have a negative divided by a positive, that's a negative. Another negative divided by a positive, another negative. So f prime is negative in both intervals, which means the original function f is decreasing in both intervals. Okay, so it's doing something like this and like this. So there's no sign change here. We are looking for a relative extrema, like a max or a min. If we were going to have a relative min, we'd want f of x to be decreasing and then increasing. Then we'd have a min. Or if it was increasing and then decreasing, then we'd have a max. But if it's decreasing and decreasing, if f prime is negative and negative, then there is no relative max or min. We can say f of x has no relative extrema because f prime does not change signs. One more thing. We knew, if you're paying attention, we knew from the start that you could not have a relative max or min at x equals 1 because that's where the original function is undefined. You can't have a max or a min where the function is undefined. So just another thing to watch out for.